Welcome back to the Deep Dive. Today, we are on a pretty critical mission, I think. We're tracking how large language models, LLMs, are kind of breaking out of their text boxes.
Yeah, that's a good way to put it.
We're looking at the foundational techniques that are transforming them from these incredibly smart, reactive chat partners that only talk into proactive, goal-seeking assistants that can actually do things in the world.
Exactly. And, previously we spent some time on what we call reasoning models.
Right, the ones that generate a hidden chain of thought before they give you an answer.
That's the one. And that move was all about improving how the model thinks internally. But even those models, the really powerful ones, they still suffered from two pretty fundamental limitations.
Right. If you looked at the state of the art even just a year ago, the models were brilliant, but they were stuck. Their knowledge was completely static.
Yeah.
It just stopped the day their training data was cut off.
Yeah.
And the second major weakness was, well, they had no external access. They couldn't do anything beyond just generating text.
And that's the barrier we're breaking today. We have a really dense stack of sources, and our mission is to unpack the three major techniques being used to solve this.
Okay.
First, retrieval-augmented generation, or RG. Second, structured tool calling. And third, the fully autonomous, iterative workflow of agents.
Let's unpack this, and I think we have to start with that knowledge cutoff problem.
Yeah.
Because it's just a constant headache for developers.
Oh, it's a huge dilemma.
You train your incredibly expensive, powerful model, but if a major event like an election or a new product launch happens 2 weeks after your training deadline, your model is instantly out of date.
It is. The knowledge is static, and the sort of natural knee-jerk solution...
Just retrain it.
Just retrain the whole model.
Right.
But that's nearly impossible. It carries this high risk of what's called catastrophic forgetting, where you actually make it worse on things it was already perfect at.
Right.
And for companies that are maintaining, dozens of these fine-tuned models, the maintenance overhead is just astronomical.
So the very first sort of naive attempt to fix this was what I call context cramming. You just take all your new documents, all your company's internal memos, the news articles, and just stuff them right into the LLM's input prompt.
Which fails. And it fails quickly for about three main reasons. First is context length.
It's still finite.
It's getting bigger, but it's still finite.
Yeah.
You might get, say, 400,000 tokens in a huge model, but that's your limit. You can't fit the whole internet or even a medium-sized company's entire knowledge base into every single query.
And even if you could somehow cram a small library in there, you run straight into the infamous needle in a haystack problem.
And this is where it gets really counterintuitive. Research has shown again and again that when you give an LLM this massive prompt with one crucial piece of information, the needle, surrounded by a sea of junk,
The haystack.
The model's performance actually goes down substantially. It just gets overwhelmed.
That's fascinating.
And what's even more fascinating is that where the needle is located matters too. If that key fact is buried early, say in the first quarter of a huge document, the model often misses it entirely.
Even though it's the first thing it reads, it's like asking a brilliant lawyer to sift through 1,000 irrelevant documents for one clause. It's just a waste of mental energy.
Which brings us to the financial argument.
Of course.
Precisely. LLM calls are priced per token, both input and output. So if you are stuffing hundreds of thousands of tokens of context into every single query, your costs, they just multiply instantly.
So it's a performance failure, and it's a financial failure.
Absolutely.
Which is why the industry landed on the architectural solution, retrieval-augmented generation.
The elegant fix.
It's the elegant fix where we decouple the LLM's vast reasoning capability from its static knowledge base. RAG doesn't put all the new information in the prompt.
No.
It figures out which few paragraphs are relevant and only uses those to augment the query.
And that retrieval step, that is the entire ballgame. To support this, you first have to pre-process your knowledge base. You take your documents, divide them into small chunks, maybe 500 tokens or so, and then you compute a vector embedding for each chunk.
So you're turning text into a numerical address in some huge semantic space.
That's it. And if the knowledge base is massive, maybe millions of these chunks, we can't compare the user's query against every single one every time.
It would be too slow.
Way too slow. So the retrieval process is usually split into two optimized stages. It's a lot like Google's search architecture, actually.
Okay, so what's stage one?
Stage one is candidate retrieval. The goal here is just speed and maximizing recall. We want to quickly filter millions of chunks down to a pool of a few hundred potential candidates.
And how do you do that fast?
We do it by calculating semantic similarity, so how close the user's query embedding is to the chunk embeddings, using methods like approximate nearest neighbor or ANN to keep it lightning fast.
That makes sense.
Yeah.
But semantic similarity can sometimes be too clever for its own good, can't it? Like, if I search for a code name, say Project Bluebird, a semantic search might give me documents about Project Robin, because they're both secret bird projects.
But you needed Bluebird.
I needed the exact keyword Bluebird to get the right document.
That is a critical limitation. And it's why high-end RAG systems use what's called hybrid search.
Okay.
They combine the power of that semantic embedding search with classic heuristic keyword matching, like the BM25 algorithm, to generate a single, more robust relevance score.
So you get the best of both worlds, conceptual similarity, and exact keyword matches.
Exactly. So now you have your hundreds of candidates, and you can slow down a bit and focus on maximizing precision. That's stage 2, re-ranking.
Right.
Now we can afford to use a more computationally expensive method, usually a cross-encoder setup. So instead of having 2 separate models making 2 separate embeddings, the cross-encoder takes the query and the candidate chunk together.
It looks at them at the same time.
Right. It analyzes them holistically and produces a final, highly accurate relevance score. And since we're only doing this on a few hundred candidates, the efficiency holds up.
Now, developers are always looking for ways to squeeze more relevance out of Raj. You mentioned a couple of advanced tricks that stood out in our sources.
Yeah, the first one addresses this mismatch between a short user query and, a long 500 token document chunk. The solution is subtle. Before you embed the query, you have a small language model expanded into a hypothetical fake document that's longer and more descriptive.
So you're using an LLM to generate a better search query for another LLM.
You are. It's wonderfully meta.
That's great. What's the second trick?
The second trick addresses the problem of chunks being retrieved out of context. If a chunk is pulled from the middle of a long document, it might lose its meaning.
I see.
To fix this, you can use an LLM call to prepend a short context summary to the start of the chunk before you embed it. Now, generating the summaries can be expensive, but you can mitigate the cost by using prompt caching for that recurring prefix.
So if I'm a developer building this system, how do I actually measure if my fancy new hybrid search and re-ranker are working? How do I quantify success?
You'd turn to standard ranking metrics. The most sophisticated one is probably NDCG at K.
Okay, what does that stand for?
It's a normalized discounted cumulative gain. It's great because it cares about 2 things: relevance and position. It gives more credit for relevant documents that appear higher up in the ranking.
And then there's MRR.
Mean reciprocal rank. This is the metric that a traditional search engine loves most.
Yep.
It only cares about how high up the first genuinely relevant document appears. For a lot of users, if that first result is good, they stop searching.
So MRR is a quick measure of immediate satisfaction.
Exactly. We also use things like precision at K and recall at K, but really NDCG and MRR give us the clearest picture of retrieval quality.
Okay, so Ari has solved our knowledge problem. We can now access current, massive, evolving data sets without retraining our base model. But the other limitation you mentioned was the inability to act. We fixed the brain, but the LLM still doesn't have any hands.
That's the perfect segue into tool calling. This is the second monumental step. We're now introducing external structure.
Okay.
Tool calling allows these autonomous systems to complete complex tasks by dynamically accessing and, acting upon external resources. Critically, this works with structured data specifically, functions or APIs.
Which is why you often hear it called function calling.
Exactly.
This completely shifts the LLM's job description.
Mm.
It stops being a pure text generator and starts being a prediction engine for function arguments.
That's it.
Let's use that classic example from our sources.
Yeah.
The user wants to find a teddy bear near them.
Right. A vanilla LLM, trained only on text, would just say something like, "I apologize, I cannot access real-time location data." But with tool calling, it's a 3-stage choreographed process.
Okay, stage 1.
Stage 1. The LLM gets the user query, "Find a bear near me," plus the full definition of the external API function, say, "Find teddy bear, location, radius."
And the LLM's new job is to analyze that query and predict the necessary structured arguments, maybe the user's coordinates and a 1-mile radius, and output that in a format like JSON.
Then you have stage 2, which is entirely external. The LLM steps back. That JSON output is executed by a separate backend system. The API call goes out, hits the external database, and returns a structured result.
Also in JSON.
Yeah, probably a JSON object containing the bear's name, its distance, and its current mood, hopefully happy.
In stage 3, the LLM takes that structured JSON result and formats it back into a polite, natural, human-readable response. I found a happy bear named Cuddles 2 blocks away from you.
It's a closed loop, but the LLM only does the prediction and the final presentation. It never actually executes the code.
So what does the model actually need to learn to shift from predicting text to predicting an API call and structured arguments?
Well, there are two core methods for teaching this. The first and most traditional is supervised fine-tuning, or SFT.
Ah.
You need two distinct sets of training pairs. One set trains the model on mapping the user query to the correct function arguments, predicting the JSON.
And the second set.
The second set trains the model on how to correctly map the conversation history plus the structured JSON result back to a pleasant final output.
That sounds complicated and very data-intensive. What's the second approach?
Prompting. You simply provide the function API to the LLM alongside a very detailed, highly optimized explanation of its usage, its limitations, examples, everything.
Wait, I remember this detail from the source. We don't write that detailed explanation ourselves, do we?
Absolutely not, because that's the hard part. This is where we use one LLM to write the instructions for another LLM.
Of course.
You use a separate, powerful reasoning model to iterate on those prompt instructions, feeding it evaluation results, successes, and failures, until the prompt is perfectly optimized to teach the target LLM how to use that function correctly.
That's one of the most powerful meta techniques I've heard of. And tool calling quickly scales up the use cases, right? You get information retrieval like weather or search.
Computation, where you turn a math query into executable Python code.
And critically, action like using an API to send an email or file an expense report for you.
But here's the major scaling challenge. What if you have hundreds of tools?
You run into context length issues again.
And performance goes down because the LLM is just overwhelmed trying to pick the right tool from this massive list.
So we need another layer of RAG, but for tools this time.
Precisely. The solution is tool selection, or routing. You use a separate system, a router that looks at the query, and a very brief, bare-bones description of all the available tools. That router picks only the 2 or 3 relevant ones.
And only those get fed to the main LLM.
Right. It saves context and increases performance dramatically.
And to standardize all of this tool access across different models, Anthropic stepped in with the Model Context Protocol, or MCP.
Yes, the MCP is an effort to standardize how tools are defined and accessed. It specifies components like the MCP server, the tools, the prompts, and external resources. Think of it like this.
Instead of reinventing the wheel for every new LLM.
Exactly. This protocol ensures that a standard tool for, say, checking stock prices can be accessed seamlessly by GPT-5, Claude, or any other compliant model.
So we've solved set acknowledge with RAG, and we've enabled single structured actions with tool calling. The next logical step, and our final topic, is combining these into something truly autonomous: agents.
An agent is the culmination of all this. It's defined as a system that autonomously pursues goals and completes tasks on a user's behalf.
And the critical difference from simple tool calling is, what? The loops.
It's the embedded reasoning and the iterative recurrent loops. They break a complex, multi-step goal into manageable pieces, and they just keep looping until the goal is achieved.
The blueprint for this seems to be the React framework Reason and Act.
Yes, it decomposes complex goals into 3 stages: observe, plan, and act.
Let's go back to our teddy bear, but this time, the bear is cold.
Okay, so the agent starts the loop. Observe. It has to translate the user command, "my teddy bear is cold," into a need to know the current room temperature, which is an unknown.
So it plans.
It plans. Plan, determine the room temperature. Act. Call the available tool. Get current room temperature.
The tool then returns the result, 65 degrees Fahrenheit.
Now the loop repeats. Reobserve. Okay, 65 degrees is too cold, so the goal of comfort is not met. Replan. Need to increase the temperature to 72 degrees. React. Call the adjust temperature to tool.
And it keeps going.
It continues this cycle of observing the result and planning the next action until that ultimate goal is satisfied.
The moment you have these complex agents pursuing goals, you also have the need for them to coordinate with each other. Agent-to-agent communication.
Right, and Google addressed this with the agent-to-agent, or A2A protocol. It standardizes how one agent tells another agent what skills it exposes, like maintain comfort for our thermostat agent, and standardizes the execution methods, like execute or cancel. They need a common language.
This is where the engineering complexity skyrockets. But also the security risks.
Massively.
Because agents are designed to execute actions in the real world,
Yeah.
sending emails, querying databases, running code. The safety imperative is just critical.
It is the most important consideration in this entire field. The potential for unintended harm is huge. A classic security threat is data exfiltration.
How would that work?
Well, imagine an agent is equipped with a tool to send an email. If it's tricked, through a multi-step prompt, into writing a user's sensitive password, which it has temporary access to, into that email, it has just leaked sensitive information into the real world.
That's terrifying. How are developers mitigating this possibility?
The mitigations fall into two classes. The first is training stage safeguards, using advanced fine-tuning and reinforcement learning to actively train the agent on harmlessness, making it refuse malicious requests.
And the second class?
Inference stage safeguards, using separate safety classifiers that check the agent's reasoning chain and its proposed action before the tool is ever allowed to run.
And there are benchmarks for this now.
Yes. Benchmarks like Agent Safety Bench are now essential for measuring this capability.
And this isn't just theoretical. Our sources cited that recent report from Anthropic about disrupting a real-world AI-orchestrated cyber espionage campaign that was using these tool and agent capabilities.
Yeah, to achieve complex, multi-step infiltration. The threat is here. It's real.
It is. So for anyone out there building these agentic workflows, the development advice we saw was pretty consistent.
Start small and simple, and use the most capable models first. Start smart to establish a high-performance baseline before you try to optimize for size or latency.
And perhaps the most useful piece of advice for transparency and debugging, just watch the chain of thought.
Absolutely. The models output reasoning chains for a reason. Prioritizing transparency and debuggability means observing those chains. If the agent makes a mistake, the error is usually right there in the plan, allowing developers to quickly understand and fix the logic flaw.
This entire deep dive has taken us on quite a journey. We moved LLMs from a static text box, solved the knowledge problem with RAG, gave them external capability with tool calling, and finally enabled autonomous goal pursuit with these agentic loops.
These systems are profoundly changing how we approach complex tasks. For instance, our sources noted that AI assistant coding, where agents handle all the complex piping and code generation, is a developer favorite.
Why is that?
Because it dramatically frees up the mental load associated with all that boilerplate code.
And yet, as powerful as generating code or planning a complex action becomes, there is this fundamental human job that remains the bottleneck, isn't there?
There is.
Generating the code or generating the plan is quickly becoming cheap and easy, but judging whether that generated code is correct, and maybe more importantly, whether it does the right thing relative to the user's intent and safety boundaries, that is still the hard part.
That human expertise, that ethical judgment, it remains the most valuable commodity.